Welcome to EPG Pathshala lectures on numerical methods. Today we are going to talk module 1 on interpolation, introduction and Lagrange interpolation. So, this will be in part 1 of this, and part 2 will be the module 2. In this, the learning objectives are introduction to interpolation, relevance of interpolation and Lagrange interpolation. These are the three main learning objectives of these modules are. Why interpolation? Because whenever you learn any new technique, the first question comes, why we should learn this technique. So, there are many real situations in which a process phenomena is observed at certain intervals of time, and sometimes it may be difficult or impossible to observe or record such process continuously. However, in some cases it is required to know the status of the process at some instance within the period over which the observations are recorded. To understand this, let us take two examples. The first example is the population census of the country. Suppose we consider, you know that a population census of a country is taken after every 5 to 10 years, say in 1995, 2000, 2005, 2010 and 2015. And suppose the government wants to know the effectiveness of certain populist measure in 2009, for which the estimate of population in 2009 is required. Example 2 is the black and white digital image we are talking about. In a black and white digital image, various gray levels Z are recorded at certain grid points depending on the resolution of the image, and to get exact analog image, gray level estimates at the intermediate positions or a functional representation of the gray level, say z equal to g x y at a positional point x y is required. So, these are the processes where you always need something which is not already available in the data. So, in general there are two types of variables associated with the process. One, a dependent variable, that is population or gray level as we have seen in the illustration, and an independent variable, year or coordinate of a point. This is what we are doing. The observations are recorded in the form of values of the dependent variables corresponding to the certain discrete values of the independent variables. The technique of determining the values of dependent variable at some intermediate values of the independent variable, that is values in the domain over which the observations are made from the observed discrete data points, is called the interpolation. If the various if values of the dependent variables are required to be determined at the values of the independent variable outside the domain of observation, then the technique is called the extrapolation. So, if we are requiring the values to be determined within the domain of observation, it is interpolation. If it is outside the domain of observation, it will be extrapolation. Polynomial interpolation is a kind of a specific case of interpolation in general. Suppose a parameter y, that is dependent variable, say temperature on the central shaft of the electric motor of length L is measured at various positions determined by distance x, where that is independent variable, from one end point of the shaft, and suppose that these positions are identified by x equal to x 0, x 1, x n, where maybe 0 is equal to x 0 is less than x 1, that is 0th position is length 0 is x 0, x 0 less than x 1 less than up to x n equal to L. Thus, we have a data of the form in the form of table we are writing. The first row gives us independent variable, which is starting with x 0 and so on and so forth x I x n, and the second row gives us the dependent variable y 0 and so on y I y n. Our problem is to determine the functional relationship between the parameters y and x. That is to determine function f such that y is equal to f x for all x in the interval 0 to L, where 0 is the first coordinate and then first point of the shaft from where the measurements are beginning, and L is the last point on the shaft, which satisfies y I equal to f x I for I equal to 0, 1, 2, 3 up to n. So, this is what our objective is. So, we want to determine the functional relationship between x and y in terms of f x. So, we are trying to do that. Most convenient guess for the function f is a polynomial function p. This relationship is not known in advance, and therefore, we are guessing that what kind of relationship this will be, and the most convenient guess for the function f is a polynomial p, which is of the form p x is equal to a 0 plus a 1 x plus up to so on n minus 1 x raised to n minus 1 plus a n x raised to n, for which the n plus 1 unknowns a 0, a 1, a 2, a 3, a n can be uniquely determined by the n plus 1 conditions, which are given by f x I is equal to y I, which we are considering it to be equal to p x I for I equal to 0, 1, 2, 3 up to n. So, we are saying that the functional relationship that f x should pass through the given data points. So, at x I my p x value and function value should be same. Now, such a polynomial function of degree n is geometrically represented by a curve that passes through the n plus 1 points x I y I equal to 0, 1, 2, 3 up to n. Technique of determining such a polynomial function representing the observed data points is called as a polynomial interpolation. So, in general, if you are just trying to determine some functional relationship, it is interpolation. If you are trying to determine relationship in the form of a polynomial, it becomes a polynomial relationship. So, polynomial interpolation. This graph shows that how the x values are plotted along x axis, y values are plotted along y axis, and then we have got these are the data points are given on the curve that represents there, and this is the interpolating polynomial curve, which is passing through exactly through all the data points. What is the historical perspective of interpolation? See, it is around 300 BC, ancient Babylon and Greece were using linear as well as more complex forms of interpolation to predict the positions of the sun, moon and the planets they know of. In 625 AD, Indian astronomer and mathematician Brahmagupta introduced a method for second order interpolation of the sine function, and later on a method for interpolation of unequal interval data. Then in 1675, Newton began his work on the subject, which laid the foundations of the classical interpolation theory. In 1795, the Lagrange published the interpolation formula now known under his name, and in 1913 to 23, Sir Edmund Whittaker, a professor of numerical mathematics at University of Edinburgh, observed that the most common form of interpolation occurs when we seek data from a table which does not have the exact values we want. For example, when you are talking about our first illustration of population, population was available at all the points 1995, 2000, 2005 and so on and so forth, and we wanted population in 2009, which the data is not available. So, that is what it means here. Mathematical facts about population function polynomial functions. What we are trying to do here is we are trying to first understand what are the polynomial functions, what are their mathematical characteristics, so that we can better understand the polynomials and use it for our purpose, that means for interpolation purpose. Now, when you are given a polynomial a 0 x raised to n plus and so on and so forth, and if a 0 is different from 0, then we say that p x is the polynomial of degree n. There is always a unique polynomial of degree less than or equal to n passing through n plus 1 points x I, y I equal to 0, 1, 2, 3 up to n, where x 0, x 1, x 2, x 3, x n are distinct numbers. So, given data points are n plus 1 data points. Through n plus 1 data points, there will be unique polynomial of degree less than or equal to n passing through this. This is what we are claiming. That is the first property of the polynomials that we are considering. The fundamental theorem of algebra states that a polynomial p x of degree n with real coefficient has exactly n possibly multiple complex roots, Say these roots are r 1, r 2, r n are distinct roots with r 1, r 2, r k are distinct roots with multiplicity m 1, m 2, m 3, m k, then sum of the multiplicities will be equal to n, and your polynomial p x can be represented as a 0 into x minus r 1 raised to m 1 into x minus r 2 raised to m 2 and so on. This product continues up to x minus r k raised to m k. So, each factor appears to the degree of its multiplicity. Mathematical facts about polynomial functions we are continuing further. So, if we consider the set P n of all polynomials of degree less than or equal to n, now we are putting algebraic structure on that. Under the pointwise addition and scalar multiplication, then P n is a vector space over the field of real numbers, because all coefficients are real. So, if we add two polynomial functions point by point, pointwise, then that pointwise addition we are considering, and scalar multiplication means you take any constant alpha times polynomial p x. So, that is again a polynomial function, and this P n under these two operations forms a vector space. Now, as you know that every vector space will have some kind of a dimension, that is the number of elements in its basis if it is finite dimensional. So, the space P n is of dimension n plus 1, and the set of functions, for example, we can say 1 x, x square up to x raised to n. So, each individual is a function, 1 is constant function 1, x is function f x equal to x, x square and so on and so forth. All these functions it is its usual basis. So, usually P n has we consider in the form of a 0 exponential, that is with respect to this particular basis. In the sense that the polynomial p x in P n is expressed as a linear combination of these functions, and thus we get p x equal to a 0 plus a 1 x plus up to a n x raised to n, where a 0, a 1, a 2, a 3, a n are all are some real constants. Apart from the usual basis, there are number of other interesting basis for P n. For example, we consider another basis say B 1, which is given by 1 comma x minus x 1 x minus x 0, then x minus x 0 into x minus x 1. So, this is a quadratic polynomial, first is first degree polynomial, first is constant 1, second is first degree polynomial, second is second degree and so on and so forth, and last is going to be the product of all the factors x minus x 0, x minus x 1 up to x minus x n, where these are the x 0, x 1, x 2, x n are the some constant which are distinct from each other, we are saying. then that also will work as a basis for the Pn. The third basis which I am indicating here is just in the reverse order, we are taking those points x n, x n minus 1 and so on and so forth. Then B2 will be of the form 1 x minus x n alone, then x minus x n into x minus x n minus 1, and you go on adding one factor every time, and we get final that last function as x minus x n into x minus x n minus 1 into x minus x 1. So, these are the n plus 1 functions which will also form a basis. The very special basis is there, that is called B3, which is given by ln 0 x, ln 1 x, ln n x, where ln j x, because n is fixed here, n is degree, I mean n is P n is because all n degree polynomials less than n degree polynomial we are taking. So, n is fixed here. So, n j will change the function. So, ln j will give me the numerator as x minus x 0 into x minus x 1 up to so on x minus x j minus 1, and x minus x j factor is dropped, and x minus x j plus 1 up to x minus x n. And in the denominator you are just repeating numerator by replacing x by x j. So, denominator will be x j minus x 0, x j minus x 1 up to x j minus x n. Naturally, x j minus x j cannot be the factor in the denominator, as it will be 0. So, if such functions also will form a basis for P n. So, we can see that P n, any polynomial, can be represented in terms of different bases in a different form, which is what we are indicating here. So, thus any polynomial P x in P n can be expressed in number of 3 different ways or different forms using these bases. For example, P x, if I write from the in terms of basis B 1, then I will get it as B a 0 plus a 1 x minus x 0 plus a 2 x minus x 0 into x minus x 1 and so on. Second will be P x equal to a 0 plus a 1 into x minus x n plus a 2 into x minus x n into x minus x n minus 1 and so on. And third, P x equal to a 0 L 0 x plus a 1 into L 1 x plus a n into L n x, like that we are considering. So, these are the various forms of the polynomial representation. So, it is important to note that all these forms are mathematically equivalent, except that the values of the coefficients a 0, a 1, a 2, a 3, a n are different in different forms. Now, what are the interpolating methods here? We are considering interpolating methods as depends on the form in which the P x is represented, as well as on the information that the data points are equally spaced or not equally spaced. So, interpolation methods differ depending on which basis you are using for representation of a polynomial, and secondly on the data set that we are given, which are equally spaced. If they are equally spaced, some techniques will be used. If they are unequally spaced, some other techniques will be used. Main objective of each method is to best utilize the information available and determine the interpolating polynomial with computational ease. So, it should be easy to compute these polynomials. So, most commonly used interpolating methods are Lagrange interpolation, Newton's divided difference interpolation method, Newton's forward difference interpolation method, and Newton's backward difference interpolation method. So, these are the 4 methods that we will be studying during the course of our lectures. So, given n plus 1, this Lagrange interpolation when we are talking about, given n plus 1 distinct data points x I y I for I equal to 0, 1, 2, 3 up to n, with a equal to x 0 less than x 1 less than x n minus 1 less than x n equal to b, the problem consists of finding out a polynomial P x of degree n such that P x I is equal to given data value y I for all I equal to 0, 1, 2, 3 up to n. So, we say that the polynomial P interpolates y n at the nodes x I, that is what it will mean. So, as mentioned earlier, such a polynomial p is in the space P n and hence can be expressed in terms of the some basic functions. In Lagrange interpolation method, we use the basis B 3, which is given by ln 0 x, ln 1 x, ln n x, where ln j is as defined earlier. Thus, our problem is reduces to finding a 0, a 1, a 2, a 3, a n such that p x, which is equal to a 0 ln 0 x and so on up to a n ln n x, and p x I is equal to y I for all I equal to 0, 1, 2, 3 up to n. So, we are given n plus 1 conditions and we have to determine n plus 1 unknowns a 0, a 1, a 2, a 3, a n, and these conditions are now we can determine depending on the properties of ln j. So, what are the ln j's? Ln j x j, if you consider ln j x j, that will be equal to 0. If I ln j x I we are talking about, ln j x I will be equal to 0 if I is not equal to j, and ln j x j will be equal to 1. You can look at the form of the ln j, and from that we can easily deduce these facts about ln j. So, ln j x I, so j and I are different, then that will be 0 and ln j x j will be equal to 1. Hence, p x I, so now if you substitute these values of x 1, x 2, x 3, x n in the p x representation, then we will see that p x I will be equal to a I and a I into ln j ln I x I actually sorry. So, hence p x will be equal to a I into ln I x I, which is equal to a I, and hence the condition p x I equal to y I for I equal to 0, 1, 2, 3 up to n gives us that a I will be equal to y I for all I equal to 0, 1, 2, 3 up to n. Thus, the Lagrange interpolating polynomial is given by p x equal to y 0 into ln 0 x plus y 1 into ln 1 x plus up to y n into ln n x. So, each of these a i's are now replaced by y i's, and that is because of special form of ln j. So, by Lagrange's interpolating formula, we are approximating the function y x by a polynomial of degree 3 on the interval 0 to 2 using the given 4 data points, and this polynomial will be given by y x equal to 0.0 into L 3 0 x plus 0.57 into L 3 1 x plus 1.46 into L 3 2 x plus 5.05 into L 3 3 x. If we write now these values of L 3 j's, then we will get the expression like this. So, 0 first is 0 because coefficient is 0. So, we start with the second term. So, 0.57 into L 3 2 we are now writing. So, we will get here L 3 1 we are writing. So, x minus 0 into x minus 1 into x minus 2. See, y 1 is 0.5. So, y 1 will not appear in the numerator there. So, y 1 is 0.5, 0.5 is not that factor x minus 0.5 is not appearing in the numerator here. And now 0.5 minus 0 into 0.5 minus 1 into 0.5 minus 2 will get, and similarly other two terms can be written as 1.46 into x minus 0. Now, x minus 0.5 comes in picture, x minus 1 is dropped, x minus 2, and then we get 1 minus 0, 1 minus 0.5, 1 minus 2, and in the last term 5.05 will get x minus 0, x minus 0.5, x minus 1. So, last factor is dropped, x minus 2 is dropped, and 2 comes here in the denominator. So, 2 minus 0, 2 minus 0.5, 2 minus 1. And now, putting x equal to 0.7 in this expression on the right hand side here, we get the desired value of y. At that desired value of y, we get it as y 7, y at 0.7 is given by 0.8757. since 0.7 belongs to 0.5 to 1 also, we have an option of approximating y x by a linear Lagrange polynomial on 0.51 using two data points 0.5 0.57 and 1 1.46. So, observe that 0.7 is lying in 0 to 2 as well as lying in 0.5 and 1, and because now in 0.5 and 1 in this interval we have got only two values, we can approximate it by a linear polynomial interpolation, linear Lagrange interpolation, a polynomial on this interval 0.5 to 1 using two data points this, and that can be obtained very easily as y x equal to 0.57, because value at 0.5 is given by x minus 1 upon 0.5 minus 1 plus 1.46 into x minus 0.5 upon 1 minus 0.5, and that will yield us y equal to 0.7, which is given by 0.926. Again we can observe that 0.7 also lies in the interval 0 to 1 and 0.5 to 2. Now, in both these intervals we have three data values given to us at 0, 0.5 and 1, and in the other case we have got 0.5, 1 and 2. So, there are three values everywhere, and hence we may approximate y x by quadratic, that is second degree Lagrange polynomial on the interval 0 1 as well as on the interval 0.5 2, using in the first case using three data points 0 0, 0.5, 0.57, 1 comma 1.46, and in the second case we will be using points 0.5, 0.57, 1 comma 1.46 and 2 comma 5.05 respectively. So, this is what we are doing, and for that again we write down this quadratic interpolating polynomial as y x equal to 0.57. Now, here there will be two factors because it is quadratic. So, x minus 0, x minus 1, and in the denominator we will get 0.5 minus 0, 0.5 minus 1 plus 1.46 into x minus 0 into x minus 0.5, 1 minus 0 into 1 minus 0.5, and hence I will get 0 y equal to 0 at 0.7 will be equal to 0.8876 by this formula, and in the second case we are getting y x equal to 0.57 into x minus 1 into x minus 2 upon 0.5 minus 1 into 0.2 plus 1.46 into x minus 0.5 into x minus 2 and 1 minus 0.5 into 1 minus 2, and then last term will be 5.05 x minus 0.5 y x minus 1, and denominator will get 2 minus 0.5 into 2 minus 1, and using this expression we will get y equal to 0.7 is equal to 0.8536. Now, this graphical representation shows what are these interpolating polynomials on the entire interval we are considering. So, in the first case we are getting that linear interpolation, that is linear interpolation. The second case we get quadratic interpolation, two quadratic interpolation, and you can see that there is only one intermediate point. In the first case there are only two end points. In the second case we have got 3 points, one intermediate and two extreme points. In the third case also the same, because it is quadratic interpolation, and in the third case it is cubic interpolation, therefore, we get two intermediate points and two end points. So, that is how we are getting this four polynomials represented graphically in this, and from graph also if you look at the at 0.7, if you take x to 0.7 ordinate at that point, and if it intersects this graph wherever it intersects, that will give you the estimate of y. So, in short, in this module what we have done is we have learned the concept of interpolation, polynomial interpolation and extrapolation. So, that are the three concepts we learned. Then polynomials and their properties we learned, and then finally, we learned Lagrange interpolation formula over n plus 1 distinct nodes, and we have seen some illustrations for understanding this formula in more details. Thank you.